Welcome everybody to another physics video. Thanks again to Krish Kotak for putting together this packet for us. We're gonna really delve into energy now. Energy is probably one of the most important concepts to understand in physics. If you understand nothing else really well, really understand energy, because it's really the way that everything works is through conservation of energy, especially through these equations here. How foundational energy relationship is the change in energy in the system is the external work on the system. And then the total energy of the system is mechanical plus thermal energy plus chemical energy plus, energy from friction, just so on and so forth. So the only way to change the energy of a defined system is through work done by external forces. If there are no external forces, so it's an isolated system, then total energy is conserved, or change in energy of the system equals zero. So we're going to look at a few different systems. Well, really, we're just going to look at this first scenario where a person is pushing a box, causing it to accelerate as it slides across a carpeted floor. And we're going to define it as a few different systems. First, as the box only, then as the box and the carpet, and then the person, the box, and the carpet. And we'll go from there. So, first, looking at just the box, list at least two forces doing work on the box. Well, if we draw our free body diagram, there's a force in this direction. I'm going to say that the person is pushing it to the right. So, this is the force that the person gives. There's force of gravity. There's the normal force counteracting the force of gravity, and there is a frictional force from the carpet. So, two forces I'm going to choose. I think I've listed all of them here, but I'm going to choose the friction and the person, since we know that gravity and the normal force are just going to cancel each other out. So, for each of the two forces, so friction and person, determine whether the work is positive, negative, or zero. So, the work that the person is doing is going to be positive, and the work of friction is going to be negative. This isn't just because we chose the person pushing to the right and the friction pushing to the left. It's because the work that the person does adds energy to the system, and the work of friction takes away energy from the system. And then which of these forces are external to the system? Since we're looking at just the box, so in other words, just what's happening here as internal forces, all of these forces are external to the system because we're only caring about the box. And then based on the analysis, is total energy of the system conserved? Explain why or why not. And the answer is no. This is because all of the forces are external forces. So if we go back to this statement, if no external forces act, the system is isolated, and then total energy is conserved. So for system two, we're now going to include the box and the carpet. So when the carpet is included in the system, the friction between the box and the carpet becomes an internal force. Because if you think about it, let's draw our system here. Here's the box. This is the carpet. And then here's our little person pushing on the box. And the system is everything in this circle here. So just the box and the carpet. Later on, we're going to have the person, the box, and the carpet, and it'll be the whole system. Anyways, is mechanical energy of this system conserved? Why or why not? Again, the answer is no, because the person is not included in this circle. So he is still an external force acting on the system. So energy is not conserved. And then question two, how does the inclusion of thermal energy affect the total energy balance? So a reminder that this friction converts the mechanical energy into thermal energy. And that pretty much happens pretty much every time. The reason that inclusion of or thermal energy affects the total energy balance in the way that friction, since it's an internal force, is a non-conservative force. It converts mechanical energy into thermal energy, which is non-mechanical. So by including the carpet, we can now account for heat generated by friction. energy of the system is now mechanical energy plus thermal energy. So previously it was just all mechanical energy, and now it is like E mechanical, which is going to be the person pushing, plus E thermal, which is going to be the friction. For system three, where we're now looking at the person, the box, and the carpet, our circle now includes everything. So if we define the entire combination as our system, are there any external forces doing work? And the answer is no. There are still external forces acting on the system. Remember gravity and the normal force, but none of those forces are doing any work because they cancel each other out. So now, if we go back to our free body diagram, here's our person, here's our friction. Gravity is still an external force, but since it is perfectly counteracted by the normal force, then there are no external forces doing any work. And so the internal forces, the person and the friction, are the only things doing work. So is the total energy of the expanded system conserved? And the answer is yes. The total energy within the isolated system does not change, it only transforms from one form to another. Conceptually, where does each form of energy originate and where does it ultimately go? So, if you think about it, the person initially has chemical energy. So, we'll say chem from the muscles. That's not how you spell muscles, doesn't have an H in it. So, the chemical energy from the muscles turns into mechanical energy, which is kinetic, and then finally turns into thermal energy. So now we're going to introduce a concept called the work energy theorem, which states that the net work done on an object is equal to its change in kinetic energy. So the net work is the final kinetic energy minus the initial kinetic energy. And then this allows us to connect force applied to an object with how its motion changes. So we have a 2 kilogram block starting from rest and moving along a smooth horizontal surface. It's pushed by a variable force that changes with position as shown in the table below. And I've also drawn a very rough graph here. So you can see it's kind of like exponentially increasing. The force increases as the distance increases. And it asks us to approximate the work done by this force across the 2 meters. We can use the equation that work is roughly equal to the sum of Fi plus Fi plus 1 divided by 2 times the change in x. And then what this will give you is, let's say that this is our first change in x, which is 0.5. And we have some amount of, a force here and a force here. We can kind of draw this, and this area under the curve is going to be the work. And so for the whole system, the area under the whole curve is the work. And so we can sum all of these up. That may be an equation you're not super familiar with, so let me write it out. Or let's do an example, and I think it'll make more sense. So for the first one, we have Fi, or for the first force is 2 newtons, and then Fi plus 1, so the second force, is 3.5 newtons, and then divide that by 2. So we have 2 plus 3.5 divided by 2 times the change in x. And we start at 0 and we move to 0.5. So the change in x is 0.5. If you plug this into the calculator, you get that the work 1 equals 1.375 joules. Now, this is only working as an approximation. If you wanted to find the exact amount of work done by this force across the 2 meters, you would need to take this equation and multiply it by the distance and do some integration. But we're just looking for an approximation. So if we follow this same thing for the remaining uh, forces, so the next one would be 3.5 plus 6, and then divided by 2 and times, let's see, the distance here is 0.5 to 1 is 0.5. So we do 3.5 plus 6 divided by 2 times 0.5, and we get work 2 is equal to 2.375 joules. I'm just going to write out the rest of the works, but I trust you can do the actual equation yourself. But so that you can check your answers, work 3 should be 3.875 joules. Work 4 is 5.875 joules. And then for work total, say work total, it's just the sum of work 1 plus work 2 plus work 3 plus work 4. So the sum of all of those makes sense because of that sum sign there. Which, if you sum all of these up, you get about 13. That's just a 3. 13.5 joules as the approximate work done. So I'm going to go ahead and put that up here. Pause the video if you're still trying to check your answers. And I'm going to erase this to give me some more space. So the next question asks us to determine the velocity of the block at 2 meters. And we can use this equation, the work energy theorem. We know that the work net is equal to the change in kinetic energy. And we have our net work here. So we can say that 13.5 is equal to K initial, sorry, that's K final minus K initial. And initially we have 0 kinetic energy because the block starts from rest. And a reminder that kinetic energy is given by the equation 1/2 mv squared. So if it starts from rest, velocity is 0, initial kinetic energy is 0. So now we just have 13.5 equals 1/2 mv final squared minus 0. If you solve this equation for v, you get that v is equal to, well, mass equals 2 kilograms. So this just cancels. And we have that v is just going to equal the square root of 13.5, which is roughly 3.67 meters per second. Okay, for problem 3, we're going to delve a little bit into chemical and thermal and mechanical energy. So we have a 70 kilogram student climbing a 40-meter vertical height of stairs. And we want to answer these questions about this student. Important thing to realize first is that we know that a typical whole body efficiency for stair climbing is about 20%, or eta is the mechanical work divided by the chemical work, which is about 0.20. What this means is, or the chemical energy, sorry. So if we have chemical, the reaction of the muscles, this is going to turn into the mechanical energy plus the thermal energy. You know, muscles naturally produce heat when they work. And about 20% of that is going to, 20% of the chemical energy is actually going to turn into mechanical energy. And the remaining 80% is going to turn into thermal. So, first question, we want to compute the increase in gravitational potential energy. We have a 70 kilogram student climbing 40 meters. And so we know that the change in potential for gravity is just going to be mg delta h, which will be 70 times g, which is 9.8, times the change in height, which is 40 meters. So that is, let me see, 27,440 joules. Question 2 says using eta is 0.20, find the total chemical energy the body must supply for this increase in gravitational potential energy. So we know that, man, I cannot draw in eta very well. I think that's an eta. I think it's a lowercase eta. But we know that eta is the mechanical energy divided by the provided chemical energy. So we can rearrange this to say that the chemical energy equals the work from the mechanical energy divided by our eta. And we know that it's going to take 27,440 joules of energy to bring the student up those stairs because that's how much potential energy they have at the top. And so we can say that our Echem equals 27,440 divided by 0.2, which equals 137,200 joules, or 32.8 kilocalories. And then I should point out that for kilocalories, kilocalories is the energy divided by 4184 is the factor for changing that. All right. Question 3 wants us to determine the amount of energy released as heat. Let me section this off. So we have that the energy from heat is going to equal the chemical energy minus the mechanical energy from this equation right here, where chemical energy essentially equals mechanical energy plus thermal energy. And so our heat or thermal energy is chemical minus mechanical. And so we have, if you plug in our chemical as this number and our mechanical as this number over here, the thermal energy is 109,760 joules. And then this turns into, using our kilocalorie calculator up here, it is about 26.2 kilocalories. And then the last question says if the student took a minute to climb the 40 meters, calculate the average power output. So we first have the average power output for the mechanical energy, which is going to equal the work from mechanical energy. That's work ME divided by time, which is our 60 seconds. We know work ME, we know time is 60 seconds. So if you plug those in, you get about 457 watts. And then for the metabolic rate, the average power, we'll just say chem, is the chemical energy divided by time, which plugging this value in for chemical energy and 60 seconds in for our time, we get about 2.29 kilowatts. Okay. The next problem, we're now going to deal with combining what we've learned about conservation of energy with what we already know about conservation of momentum. Reminder that conservation of energy essentially says that E total equals the sum of EI from I equals 1 to N just being however many energies we have. And then conservation of momentum essentially says that MIAI, or VI, sorry, equals M final, V final. And then so initial mass and initial velocity equals final mass and final velocity. And then you can add on however many, like if you got two masses, then it's like this. I'm not writing this out very well. There it is. So that's what we're working with. So we have a 5 kilogram bowling ball traveling at 10 meters per second when it strikes a stationary 1 kilogram bowling pin. Assume the collision is perfectly elastic and head on. So we start with, first let's write our conservation of momentum equation. So I'm going to say the bowling ball is object A and the bowling pin is object B. So we have the mass of A times the initial velocity of A plus the mass of B times the initial velocity of B. And then this is going to equal mass of A times final velocity of A plus mass of B times final velocity of B. So this is equation 1. Equation 2, we do the same thing for the kinetic energies. So 2, we have 1/2 MA VAI squared plus 1/2 MB VBI squared. And then this just equals 1/2 MA VB final squared plus 1/2 MAV. All right, this is an A. And then VB final squared. So these are our two equations. And we can already start plugging in values and getting rid of things. For example, we know that here, we know that VBI is 0 because the 1 kilogram bowling pin we can assume is at rest initially. So this is 0, and then equivalently, this one down here is 0. So we already know that. And then let me give myself a little more space here. Plug in the rest of the values. We know the initial mass of A is 5, and the initial velocity of A is 10. So 5 here, 10 meters per second here, we have 50 equals the mass of A, which is 5, times the final velocity of A, plus the mass of B, which we know is just 1, times the final velocity of B. So that's one equation. The next one, we have 1/2 MA VAI squared, which if you plug in 5 kilograms for the mass and 10 meters per second for the velocity, you get 250. And then this equals 1/2 times 5 for the mass. So that's 2.5 VA final squared plus 1/2, and then the mass of B, missed that there, is the bowling pin is just 1 kilogram. So 1/2 of 1 is 0.5 VB final squared. Okay, this doesn't look near as scary now. We have two equations and two unknowns. So now we can just do simple algebra to solve. So for this, I'm going to solve for VB final. We're going to say VBF equals 50 minus 5 VAF. And then I can take that and plug it in for VAF right there. So we end up with 250 equals 2.5. Or sorry, I'm plugging it in for VBF, not VAF. So 2.5 times VAF squared plus 0.5 times 50 minus 5 VAF squared. So let's first expand this. So we have 250 equals 2.5 VF squared plus 0.5. And then if you expand this, you get 2,500 minus 500 VAF plus 25 VAF squared. And then we can distribute this 0.5 to all three of those. We get 250 equals 2.5 VAF squared plus 1250 minus 250 VAF plus, let's see, 12 and a half VAF squared. So now we can do some combining. I can combine these two terms and I can subtract 250 from this side and this side. So we end up with 0 equals 15 VAF squared minus 250 VAF plus 1000. And then this is just a quadratic equation with this is our A, negative 250 is our B, and 1000 is our C. If you plug that into the quadratic equation, you get two answers. You get that VAF equals 10 and 6.67 meters per second. So how do we know which one of these is right? Well, if you go back to our initial question, remember the bowling ball is A, and we want the final velocity, VAF. The initial velocity was 10 meters per second. And if it bounces off the bowling pin and they strike elastically, it's going to make sense that it has a little bit less velocity. You know, the bowling ball is bigger than the bowling pin. It's going to cause the bowling pin to move. And so the bowling pin has to have some velocity, meaning we don't choose 10, we choose 6.67 as our VAF. So now we can just plug that in for our earlier equation we found up here for VBF. So we have VBF equals 50 minus 5 times VAF, which is 6.67. So VBF, if you do that math, is going to equal 16.7 meters per second. So now we have our two final velocities, and we have to ask ourselves, does this make sense? Well, A is the bowling ball. It has about 2.5 meters per second less velocity. And then B is a bowling pin, which is a fifth of the velocity or the mass of A was 1 kilogram. A was 5 kilograms. And it has significantly more velocity than A. And so we say, okay, yeah, I think that makes sense because the bowling pin is going to go a lot, is going to have a lot more velocity than the bowling ball. The bowling ball isn't really going to have a whole lot of change in velocity because of that. But that is the end of this problem, and there are more problems to this specific PBL, but I'm going to call it here for this one because this video is already going to be really long, and I'll post the remaining problems in another video later. But as always, thanks to Krish for making these videos, and I wish you the best of luck in your assignments.